Welcome to the Deep Dive. We're here to cut through the noise and really get to the heart of what matters in tech and AI.
Great to be here.
So today, we're looking at something that's just exploding. Agentic AI systems. I mean, the growth is staggering. Surveys are showing over half of big IT companies are actively using them.
Yeah, and the market projections are wild. Something like $5.2 billion in late 2024, heading towards maybe $200 billion by 2034. It's massive.
It really is. And traditionally, when you think about these AI agents, the foundation, the sort of brain, has always been large language models, LLMs.
Right, they handle the big thinking, the strategy, breaking down tasks. That's been the standard approach.
The source material for this deep dive, it's a position paper from NVIDIA Research, and it really challenges that whole idea.
It does, quite strongly, actually. They're not just suggesting an alternative. They're making a case that small language models, SLMs, are fundamentally better suited for most agentic tasks. More suitable, more economical.
That's a pretty bold stance given how dominant LLMs are. Okay, before we get into the why, how exactly are they defining SLM versus LLM? Small can mean different things.
That's a fair point. They define an SLM basically by practicality. Can it fit on a common consumer device like, a laptop or maybe even a phone eventually? Can it run inference quickly for one user?
Okay.
As of 2025, they're generally thinking models under, say, 10 billion parameters. Anything bigger that doesn't meet that criteria is basically an LLM in their view.
Got it. So it's grounded in real-world deployment. So our mission today then is to unpack this. We'll look at their core arguments for SLMs.
The counter-arguments they anticipate and how they push back.
The hurdles, the practical barriers stopping this shift right now, and they even propose a conversion plan, like how to switch from LLMs to SLMs.
Yeah, step-by-step algorithm. They frame their whole position not just as a recommendation, but as a necessary consequence based on community values like efficiency and sustainability.
Necessary consequences.
Yeah.
So what are these core value statements they make about SLMs?
There are three main ones. V1. SLMs are, in principle, powerful enough for agentic tasks. They can handle the language needs.
Okay, V1, powerful enough.
V2. They're inherently more suitable operationally, just easier to work with in these agentic systems.
V2, more suitable. And V3.
V3. They're necessarily more economical, cheaper for the vast majority of uses.
Powerful, suitable, economical. That really cuts against the grain of current LLM dominance.
Absolutely. The paper argues that using these huge LLMs is often just overkill. Agentic systems often do repetitive, narrow tasks, not really conversational stuff all the time. The LLM's massive general knowledge isn't always needed.
Right, makes sense. Let's dive into that first one then, V1. The claim that SLMs are already powerful enough. This seems like the biggest hurdle to overcome mentally.
It is a major point, yeah. They're directly challenging the bigger is better idea. They say, look, the scaling curve, how capability increases with size, it's gotten much steeper recently, meaning newer small models are getting capabilities that used to only exist in much, much larger models from just a year or two ago. You get more bang for your buck with smaller sizes now.
Okay, examples always help. What are they pointing to in the paper?
Well, they mentioned the Microsoft Phi series, Phi 2. That's tiny, like 2.7 billion parameters. But its reasoning and coding skills are apparently on par with older 30 billion parameter models, and it runs about 15 times faster.
Wow.
Then there's Phi 3 small, 7 billion parameters, which they say compares well to 70 billion parameter models of the same generation for language understanding and code.
That's a serious leap in efficiency. What about NVIDIA's own models? They must mention those.
Oh, yeah. They talk about their Nemotron H family. These use a hybrid architecture Mamba transformer, kind of interesting. Models from 2 up to 9 billion parameters are matching the instruction following and coding of 30 billion LLMs, but using way fewer computational resources, fewer FLOPs.
Fewer FLOPs, so less cost, less energy.
Right. And maybe even more striking, they mentioned the DeepSeek R1 Distill series. One of those, a 7 billion parameter model, apparently outperforms even big proprietary models like Claude 3.5 Sonnet and GPT-4o on some common sense reasoning benchmarks.
Outperforms them, not just matches.
On specific benchmarks, yes. That's what the paper notes. It really hammers home the point that size isn't the only thing that matters anymore.
So it's not just the base model capability, but you can also enhance them.
Exactly. That's another key point. You can boost SLM reasoning at inference time. Techniques like self-consistency, where it generates a few answers and picks the most common one, or tool augmentation, teaching the model to use external APIs or tools.
Right, like giving it a calculator or letting it search the web.
Precisely. They cite Toolformer, which is only 6.7 billion parameters, but it actually beat GPT-3, which is massive at 175 billion, on certain tasks because it learned to use APIs effectively.
So the takeaway is that for many agent tasks, you just need a certain level of capability, not necessarily a gigantic model behind it.
That's their argument, yes. Capability is often the bottleneck, not parameter count.
Okay, the performance argument is strong. Let's talk money. V3. SLMs are more economical. How does that break down?
Well, it breaks down in a few ways. Cost, adaptability, deployment, all tilted towards SLMs, according to the paper.
Give me the headline on inference cost. How much cheaper are we talking?
They put a number on it. Serving a 7 billion parameter SLM is somewhere between 10 and 30 times cheaper than a big 70 or 175 billion parameter LLM.
10 to 30 times.
Yeah. That's in terms of latency, so speed, energy use, and those FLOPs, again, the compute cost. That makes real-time interactions much more feasible. And they mentioned things like NVIDIA Dynamo. These new inference systems are being built to handle lots of SLMs efficiently, both in the cloud and potentially on edge devices.
And fine-tuning. That's often expensive and slow for LLMs.
Huge difference there. With SLMs, using parameter-efficient fine-tuning methods, PEAFT, like LoRa or Dora, you can tweak them or teach them new tricks in just a few GPU hours.
A few hours, not weeks.
Exactly. You could literally make changes overnight. That agility is massive for agents that need to adapt quickly.
And you mentioned edge deployment. Running these on, like, my laptop.
Yeah, potentially. They mentioned things like ChatRTX, showing SLMs running locally on standard gaming GPUs. That means offline inference, which is great for speed and privacy because your data doesn't have to leave your device.
That's a game changer for some applications.
Definitely. And there's a subtler point, too, about parameter utilization. They suggest SLMs might just be inherently more efficient, using more of their parameters effectively for each task, compared to the sparse way larger models sometimes work.
Interesting. And this ties into that Lego-like idea you mentioned earlier.
It does. Instead of building one giant monolithic LLM, the idea is you build agent intelligence by snapping together smaller specialized SLM bricks.
Like having one SLM for summarizing text, another for calling a specific tool.
Exactly. They argue this is cheaper, easier to debug, faster to deploy, and just fits better with how diverse agent tasks really are. It's a more modular approach.
That modularity sounds appealing from a system design perspective. Okay, let's connect this to operational flexibility, which supports V2 and V3. How are SLMs more flexible?
Well, it stems directly from their size and lower costs. Because they're cheaper and faster to train and fine-tune, it becomes practical to actually have multiple specialized expert models.
Instead of trying to make one giant model do everything.
Right. You can spin up a new specialist SLM for a new function relatively easily. This means you can adapt to user needs faster, add new features, change output formats, even comply with new local rules without a massive overhaul.
And this leads to a kind of democratization.
That's the term they use, yeah. Democratization.
Right.
If smaller organizations or even individuals can train and deploy effective SLMs, you get more diversity in the AI ecosystem.
Which could lead to less bias, more innovation.
Potentially, yes. More perspectives feeding into development, more competition driving things forward. It opens the field up.
Another argument they make, related to V1 and V2, is how agents actually use language models. They say it's often quite narrow.
Yeah, this is a key insight. Even if you plug in a super powerful generalist LLM, the agent's specific prompt and the overall system usually only ask it to do a very specific, limited thing within its vast skill set.
Like only generate JSON output, or only answer questions about a specific document.
Exactly. So the paper asks, why use a massive LLM for that when a smaller SLM fine-tuned just for that narrow task could do it just as well, but cheaper and faster? The LLM's breadth is often wasted.
And speaking of specific outputs, they also talk about behavioral alignment, supporting V2, the need for strict formatting.
Right. Agents often need outputs in precise formats like JSON or XML, especially when talking to other software or tools. Consistency is critical.
And LLMs can sometimes mess that up.
They can have hallucinatory mistakes, as the paper puts it. Because they're trained on everything, they might occasionally output text when you need perfectly structured JSON. An SLM, fine-tuned specifically for one format, is much less likely to make that kind of error.
Better reliability for automated workflows then. Makes sense.
Yeah.
Argument 6 for V2. Agent systems are naturally heterogeneous. What does that mean?
It just means they're often built from different parts doing different jobs. So you don't have to choose only LLMs or only SLMs. You can mix and match.
Okay, like a hybrid approach.
Yeah. Maybe a powerful LLM acts as the central brain or handles really complex reasoning, but then it delegates simpler tasks or maybe conversational chat or specific tool use to specialized SLMs. You use the right size tool for each job.
Optimizing the whole system.
Exactly. More efficient, more robust.
And their final argument for V2 is about continuous improvement, using the agent interactions themselves.
Right. Agents, by their nature, get used a lot for specific tasks. Every time an agent calls a model, that interaction, the prompt, the response, the tool call is valuable data.
Ah, so you collect that data.
Securely, of course,
Yeah.
and you filter out anything sensitive, like personal info.
Use it to make the SLMs better.
Precisely. You can use this real-world usage data to constantly fine-tune your specialized SLMs, making them progressively better at their specific jobs. It creates a natural feedback loop for improvement without needing separate data collection effort.
Okay, that's a really solid case they've built. But they must acknowledge that not everyone agrees, right? What are the counter-arguments they tackle?
They do. They address three main alternative views, or AVs. The first one, AV1, is the classic argument. LLM generalists just have an inherent advantage. Bigger is better because of scaling laws and this idea of a semantic hub.
A semantic hub, meaning they understand concepts more deeply.
Sort of, yeah. The idea that the LLM size allows it to integrate information across different domains more effectively.
Then how does the NVIDIA paper push back on that?
They have a few points. First, they say scaling law studies often assume the model architecture stays the same, but SLMs are using new, more efficient architectures now. Second, scaling laws don't really capture the benefit of easily fine-tuning SLMs for specific tasks.
Right, the agility factor.
Yeah. Third, SLM reasoning can be boosted at inference time, as we discussed. And finally, they argue the semantic hub isn't as crucial for agents because complex problems get broken down into simpler subtasks anyway. You don't always need that grand, unified understanding for each small step.
Okay, what's the second alternative view? AV2.
AV2 is about economics again. It says, okay, maybe SLMs are cheaper per token, but massive centralized LLM data centers have such huge economies of scale that they'll always be cheaper overall to run.
That sounds plausible. It costs a lot to set up infrastructure for lots of little models.
It does, and the paper acknowledges this is a fair point, saying the jury is still out on this one. They admit the infrastructure and talent costs for deploying many SLMs can be significant.
But they don't completely concede.
No. They point to things that could tip the balance towards SLMs. Better inference scheduling software like their own Dynamo, making it easier to manage loads across many models, and just the general trend of infrastructure costs coming down over time, making smaller distributed deployments more viable.
Okay, so that one's still a bit up in the air. What's the last one? AV3.
AV3 is basically saying, well, maybe both worlds are possible, LLM-centric and SLM-centric agent systems, but LLMs just have a massive head start right now. Industry momentum is behind them.
Inertia, basically.
Pretty much.
Yeah.
The paper acknowledges this is possible, but they maintain their core position. The combined advantages of SLM's power, cost, flexibility are so compelling that they could realistically overcome that inertia and shift the dominant paradigm. The practical benefits might just be too strong to ignore.
So if the benefits are that strong, why hasn't this shift happened already? What are the real-world barriers they identify?
They list three main practical hurdles, not fundamental flaws, mind you. B1 is upfront investment. Huge amounts of money have already been poured into centralized LLM infrastructure, so naturally the tools and ecosystems are built around that.
Path dependency.
Right. B2 is generalist benchmarks. A lot of SLM development still chases the same general benchmarks that LLMs use, instead of focusing on metrics that show their value in specific agentic tasks.
So they're not always optimizing for the right thing.
Potentially, yes. And B3 is simply lack of awareness. LLMs get all the hype, all the press. SLMs, even if they're really effective for certain industrial uses, just don't have the same visibility yet.
So investment inertia, mismatched benchmarks, and less hype. But these aren't insurmountable.
No, the paper argues they're practical problems that are already starting to be addressed. Investment patterns can shift, benchmarks are evolving as the field matures, and awareness will grow as the economic benefits become clearer.
Which leads perfectly into the solution they propose.
Yeah.
This LLM-to-SLM conversion algorithm. How do they suggest companies actually make this transition?
It's a 6-step process designed to be relatively painless. Step 1, S1. Secure usage data collection. Basically, log everything your current LLM-based agent does internally, prompts, responses, tool calls, maybe even latency, but securely. Anonymize, encrypt.
Okay, gather the raw data on how the agent works now.
S2, data curation and filtering. Clean that data up. Most importantly, get rid of any sensitive stuff, personal information, health information, anything that shouldn't be in a training dataset. They suggest needing maybe 10,000 to 100,000 examples for good SLM fine-tuning.
Right, clean, safe data. What's next?
S3, task clustering. Use machine learning, specifically unsupervised clustering, to analyze the clean data and find patterns. What kinds of tabs is the agent doing over and over again? This identifies the natural candidates for specialized SLMs.
So you figure out, we do a lot of summarization, or we call this specific API frequently.
Exactly. Those become your target tasks. Then, S4 SLM selection. Based on those tasks, you pick the best candidate SLMs, look at their capabilities, benchmarks relevant to that task, licensing, how easy they are to deploy.
Choosing the right tool for each job you've identified.
Precisely. Then comes S5, specialized SLM fine-tuning. You take the data relevant to each task cluster and fine-tune your chosen SLMs. Use those efficient PEFT methods, maybe knowledge distillation, where the SLM learns from the original LLM's outputs.
Train the specialists. And the last step.
S6, iteration and refinement. It's not a one-shot deal. You need to periodically retrain the SLMs with new usage data to keep them sharp, adapt to changes, and maybe even retrain any router model that directs tasks to the right SLM. Keep the system optimized.
A continuous improvement cycle.
Yeah.
That seems like a very practical roadmap. So wrapping this up, the paper really lands on a strong concluding thought, doesn't it? Connecting efficiency to impact.
It does. They argue that saving money on AI infrastructure, making it more sustainable, isn't just about cost-cutting, it's an enabler. It will actually accelerate how agentic AI transforms things like white-collar work, because it makes deploying these powerful tools more feasible.
So efficiency fuels transformation.
Yeah.
And they're actively looking for feedback on this whole position.
Yeah, explicitly. They end by inviting contributions, critiques, further discussion. They want the community to engage on how to use AI resources effectively and bring down the costs. It's an open call.
So as you listen to this, it's worth thinking about what this shift could really mean. Are we moving away from this era of giant, monolithic AI brains towards something more like a bustling ecosystem? A world filled with diverse, specialized, super efficient, smaller models, maybe even running right there on your own devices.
It's a potential future where AI becomes perhaps more adaptable, more accessible, and integrated more deeply into specific tasks than ever before.
A fascinating possibility to consider. That's all the time we have for this deep dive. Thanks for joining us.
My pleasure.